Today we're going to be talking about slope fields, and we're going to start by just looking at the equation dy dx equals 2x. And, you know, we looked at this a little bit last unit, but in general, when we have an equation involving a derivative, we're going to call that a differential equation. Okay, and dy dx equals 2x. We know that that means that the slope of the graph is equal to 2x. And so I'm going to go in and I'm going to kind of describe that happening. I'm just going to pick a point. Maybe x is 1 and y is 0. So the slope there will be 2. What I'm going to do is, okay, that means that the slope would be going like that, right? Except that's going to be too much where we can't look at all of that. So we're just going to draw a little tick mark that has slope 2 that's aiming towards that point there. Okay. Over here, where at the origin, where x is 0, the slope is going to be 0. Up here, where x is 0 and y is 1, the slope is still 0. So I'm just going to fill in all of these as 0 slopes. Except I'm going to be going only out to -2 and 2. Okay, over here, where x equals 1, no matter what y is, the slope is going to be 2. That didn't look that good. I'm going to do that one again. There we go. Okay. And kind of the key is to look at the thing. There's probably a corner that you're aiming at. Like for this next one, if I'm starting here, I'm aiming at this thing. So I'm going like that. Okay. And then at 2, the slope is 4, which is really steep. That's like, you know, aiming way down there. And then just trying to do the same one each time. Over here, where x is -1, the slope is going to be -2. And then where x is -2, the slope is -4. So that's really far down. Okay, and this is a decent slope field. Before I move on and have y'all make your own slope field, what kind of equation has derivative 2x? What kind of function has derivative 2x? X squared, yes, and those things look like parabolas, and if you see it on there, well, I'll come back and talk about that in a couple of minutes. Okay, now we have the differential equation dy dx is equal to y. Okay, so the slope is just whatever the y coordinate is. And so I'm going to freeze the screen here in a second, and have y'all go out to -2 and 2 and kind of draw the slope field for that. Okay, and in the same way, I'm going to ask you the same question. What kind of function has the derivative that's the same as it? Its derivative is the same. What was it? Oh. But then that would be y dy dx. In terms of x, think about a regular function that is its own derivative. What is its own derivative? E to the x. There's another one too. And I'm going to just let y'all think about that one. I'll come back in a couple of minutes back to these examples, and I'll tell you the other one. There's another one. You can see it on there. A thing that's its own derivative. You just wouldn't think about it like that. Okay, so I'll come back and talk about that in a couple minutes. So as far as this course and the AP exam and stuff, there's really 3 things that we're going to be asked to do with slope fields. Okay, and then the sketches we made, we call those slope fields. We can be asked to sketch the slope field for a given differential equation. That's what we just did. Okay, so we're already able to do that. That's something we can do. Sketch the solution curve for a given differential equation that passes through a specific point. That's where we're going to, start at a point in the slope field, and then follow the lay of the land, so to speak. And then the third thing we might be asked to do is match a slope field to its differential equation, or vice versa. And that's what's going to show up on the multiple choice every time. It's going to be either, here's a slope field, which of these differential equations describes it, or here's a differential equation, which of these slope fields is a slope field for that differential equation. Okay, here I've got 3 slope fields. And I forgot, I needed to go back up, so I'm going to come back to these slope fields in a second. Okay, I forgot. We need to go back and do the second thing. We need to sketch the solution curve for a given differential equation that passes through a specific point. So I'm going to go back up to the previous 2 examples, and I'm going to sketch a solution curve on those. Okay, for dy dx equals 2x, we had said that a function that satisfied that was y equals x squared. Okay. Now we'll call y equals x squared a solution to the differential equation because it has dy dx equal to 2x. So I'm just going to start listing out some solutions. You may think of any other functions that have derivative 2x besides x squared?
Like plus 5.
Yeah, okay, x squared plus 5. Yes, y equals x squared. I'm going to go with y equals x squared plus 1. And maybe y equals x squared minus 2 also, right? That would also have derivative dy dx equals 2x. And so really, in general, our solution to that differential equation is going to be y equals x squared plus c, where c is some real number. Yeah, we call that the general solution to the differential equation. Okay, now that is, of course, predicated on us knowing that the derivative of x squared is 2x, and that being a pretty easy one. But that's one that we can do right now. Okay. Moreover, solution curves, say I've got one, so it might say, sketch the solution curve that passes through the point 0, -1. Okay, and so what you do is you start at 0, -1, and here the slope is flat, so I'm going to go out a little ways here, but you can see as I go to the left and the right, it's kind of curving up. So I'm going to, kind of just stay with the lines and follow the lay of the land, Oh. And there I have a solution curve. Okay. I think it is important for me to tell you that you aren't trying to jump from tick mark to tick mark. You aren't going to just go out to those 2 that are on the sides and then angle up and then go to the next ones. You're just following the general pattern. Okay, this does not have to be, an expert level drawing. This is AP calculus, not AP 2D art, right? We can sketch a solution curve. Okay, so I think let's move on to the other one. Okay, on this one we said that e to the x is a function that has dy dx equals y. So if I was writing down my solutions, I could start with y equals e to the x. We could also have negative e to the x. That's a good point. I like that one. I'm going to also, go with a kind of a weirder one and say y equals e to the x plus 1. That will also have derivative equal to itself, because the derivative of x plus 1 is just, 1. Okay, so if they asked me that f of x is some solution to dy dx equals y, with f of 1 equals 1. Okay, so I'm going to go to the point 1, 1. I'm going to follow the pattern. It seems like here, as I go to the right, it's getting steeper and steeper. And then as I go to the left, it's coming down through there. Okay. What if I said, that g of x was a solution that went through the point 2, 0? Okay, well, I would start there, but then what should I do? It's flat there, and then it looks like It's just flat everywhere. Okay, what is that the equation of? Y equals, okay, what's the derivative of 0? Okay, so there's another one that has derivative equal to itself. Okay, so y equals 0 is another solution. Now, in general, I'm going to tell you that the solution to this differential equation is y equals c e to the x, where c is some real number. But I'm going to show you why that's true in maybe next time or the time after. I'm going to leave that something for you to think about. All right, now we're ready to look at these three slope fields. Okay, there are no answer choices here. But I'll tell you, the first thing that you want to do when you're encountered with a slope field and you're trying to decide amongst multiple choices which differential equation describes it, is to see what does the slope depend on. Okay, because as I scan left and right here, I'm seeing the same slope, correct? Okay. That means that if as I go left and right, the slope is the same, dy dx doesn't depend on x. Therefore, dy dx only depends on y. Okay, over on the next one. As I go left and right, whoops. Ooh. Okay, as I go left and right, I'm seeing different slopes. So dy dx must depend on x. But then maybe I'll, kind of scan up and down. And as I scan up and down, I'm seeing the same slope. So what I'm going to say is that dy dx doesn't depend on y. And therefore, it depends only on x. And that can help us eliminate a lot of answer choices. And, let's say, depends on x only. But then over here, if you scan left and right, I'm seeing different slopes. Over here, I'm scanning up and down, and I'm seeing different slopes. This one's going to be where dy dx depends on both x and y. Okay, so we're going to be looking for x and y in the formula for dy dx. So if I was faced with this multiple choice question, I would start with, that's our first strategy, is thinking which variable does it depend on? What are we seeing here? Is it depending on x, y, or both? Both. Therefore, I can eliminate all three of the answer choices that don't have both x and y in them, and then just confidently say that dy dx equals x minus y. Now, maybe there was two of them that had x and y in it. Like something like dy dx equals x divided by y, or maybe that was a fifth answer choice. Okay, then I've got it down to 2. I have to do something else. The second strategy you want to take is to look for horizontal and vertical slopes. Okay, so I'm going to go in and I'm going to highlight where I'm seeing horizontal slopes. Now, you can't tell for sure because there's no scale on this thing. But this kind of looks like the slope is horizontal, which is dy dx equals 0, where y equals x. That's kind of, that yellow bar kind of looks like the line y equals x, where y is approximately equal to x. So if you had x minus y equals 0, that would fit this differential equation. Okay. So that's one way that you can eliminate farther. Or what would we be looking for if we saw actually vertical slopes? What would indicate that in the formula for dy dx? Yeah, undefined specifically because of division by 0. So if we'd seen anywhere where y equals 0, a vertical line, then it could have been that one. Okay, here's another one I want y'all to think about. The slope field for a certain differential equation is shown above. Which of the following could be a specific solution to that differential equation? So So they're talking about solutions here. So this is the one that you had asked about, 097. A specific solution. So the solution, oftentimes a particular solution, they give us a point. So what you want to do if they're asking for a solution is choose a point. You could choose the origin, or you could choose 0, -1. I'll choose 0, -1. And then we're going to just, follow the lay of the land, and then do something like that. And what kind of graph does that look like? Yeah, a third-degree polynomial, specifically with a positive leading coefficient. And so I could conclude that maybe it was this one. Okay, notice that this is y equals 1/6x to the third. This is not dy dx. Okay, dy dx would be, something in terms of x squared, right? Because it's always positive. Those tick marks always have positive slope. Okay, another one. Here we've got some stuff, and so you want to employ first your first technique, and then the second, and maybe then the second technique. I'm going to scan left and right, and I'm seeing, yes, as I change x, the slope is changing. Okay, I'm going to scan y. As I scan y, oh, the slope is not changing, so it shouldn't depend on y. And then you look at the answer, it's like, oh, well, I don't see anything with y in there. Okay, so your next thing is to look for horizontal and vertical slopes. And what you can't see super well is that on the y-axis, there are vertical blue marks. So what would we conclude there? dy dx equals which one? 1 over x. Because where x equals 0 on the y-axis, the slope is undefined, which manifests itself with a vertical tangent. Now, in reality, the solutions to these differential equations, if we have one of these vertical tick marks, almost always it's going to be a vertical asymptote, but not always. Okay, this one's got quite a bit of stuff going on, but I'm gonna freeze the screen and let y'all see if you can maybe figure it out. I will give you the information that I'm seeing horizontal tangents here and here, and I'm not seeing any vertical tangents, although maybe along the y-axis it could be, but I just can't see that. Okay, so the class is conjecturing A. Why are we thinking it's A? Well, let's look at some that we can eliminate. B, I think I'm going to eliminate because when y equals 0, we would need undefined slope, vertical slope, no tick marks, something like that. But I'm seeing along the x-axis actual tick marks. Okay, so I'm thinking B is out. Okay. Let's see. So we're thinking A. What about A is making us think that? Oh, okay. Well, this is kind of like the line y equals x, and this is kind of like y equals -x. For both of those, x squared equals y squared. You didn't miss much. Okay, so I eliminated an answer choice and annotated the horizontal slopes. So, okay, we're saying that x squared equals y squared for that one, and then if we squared both sides over here, we would also get x squared equals y squared. So x squared minus y squared would be 0. And that is, yeah, probably going to be enough to choose answer choice A. C, you could probably, plug in a place where, say, x squared was bigger than y squared and see that the signs were wrong or something. You could go and just choose, maybe 3, 1 or something and try to eliminate based on that. Or if you were confident in answer choice A, you could just choose it and move on.
I think it's just because there's like vertical slopes.
Oh, vertical slopes along the y-axis. Yeah, that is true. That is definitely a giveaway. Good point. Okay, next we have a free response question. And this one is from 2007 Form B. And so that would be something you could find in your free response packet. Okay, so this is a really typical slope field question. So on the axes provided, sketch a slope field for the given differential equation at the 9 indicated points. And, okay, my recommended technique for this is to make a table. And ever since probably Algebra 1, or maybe even earlier, y'all have been familiar with making this table x and y. But what I'm going to do is I'm going to add a third column, and I'm going to call that dy dx. And then I'm going to say, I'm going to start with x equals, say 0. X equals 1, and x equals -1. And then y is allowed to run from 0 to 2, so 0, 1, 2, 0, 1, 2, 0, 1, 2. And I can calculate dy dx given x and y. Okay, so I'm going to go through, and if I calculate dy dx at 0, 0, that'll be half of 0 plus 0 minus 1 is -1. I can go in and make something with slope -1. Okay, I did the arithmetic. I put them all in there. And now it's time to go and fill in the slope. So at 0, 1, the slope is 0. And what will that look like when the slope is 0? Horizontal, flat, something like that. Okay, good. At 0, 2, the slope is 1. Okay, so there we have it. At 1, 0, it's -0.5. So I need to be aiming like that. Except, you know, we don't have room to put all of those, so I'm going to put it like that. At 1, 1, it's +0.5. So it's, you know, decently shallow. And then at 1, 2, it's 1.5. So I'm kind of aiming for that point right there, and that'll be that. That might be a little steep, but I'll tell you what the readers are looking for here in a second. At -1, 0, it's -1.5. Okay, well, that looks pretty good. At -1, 1, it's -0.5. And at -1, 2, it's +0.5. Oops. Okay. Now, when you're thinking about if we were to see this on the free response section of the AP exam, what's the reader actually looking for? Are they going to pull out a protractor and measure the angle of your tick mark against the axes? No, they're not going to do that. What they're going to do is they're going to be looking at the relative slopes. The first thing they're going to be looking at is the point 0, 1. Did you do that horizontal? That's oftentimes one of the points is like horizontal or vertical slopes. Okay. Yes, we did that. And then they're going to say, okay, look at the ones along the x-axis. Did they go from steeper to less steep while still having negative slope? Yes. That's the type of thing they're looking for. So you don't have to worry about it being perfect. Now, having a little straight edge will help your slope fields look really good, you know, on the homework, on the free response, on the test, something like that. And you can use straight edge if you want, but it's not essential. We're looking for the relative steepness of these slopes. That's all we really care about. Okay, part B. Find the second derivative of y with respect to x both times in terms of x and y. Describe the region in the xy plane in which all solution curves to the differential equation are concave up. Okay, y'all take the second derivative and check your work against mine, because this is something we did the last year and it's something we should be pretty comfortable with. Yeah, that's the intro. X and y. Okay, so I took the derivative of both sides with respect to x. I got 1/2 plus dy dx, and then I substitute on dy dx to satisfy this requirement in terms of x and y only. And then I combined the -1 and the 1/2 because maybe that will help later on. Now, describing the region in the xy plane in which all solution curves to the differential equation are concave up might be a little beyond what y'all know how to do at this point, but I feel like if I show you, it'll make sense. Okay, so when they say concave up, what are y'all thinking? Positive second derivative. Yeah, second derivative positive. Okay, so I'm going to start with that. So I'm going to start with the second derivative of y with respect to x both times is greater than 0. And then I'm going to substitute on the second derivative. So that means that 1/2 x plus y minus 1/2 is greater than 0. And then maybe I'll just solve for y. And that's actually the solution. And if you think about it, from all the way back to Algebra 1, that is a region in the xy plane. Remember we graphed this, it had a y-intercept of 1/2 and a slope of -1/2, and since it was y is strictly greater than, we used a dotted line, and then since y was greater, we shaded where y was greater. And we did that just a couple weeks ago in college algebra, and so that's the region where the solution curves are concave up. Okay, next we have the is it a minimum, maximum, or neither question. And this was one that we had on the free response section of our last test. And this was one that we actually didn't do very well on. We had a lot of people appealing to the first derivative test, saying that the derivative went from positive to negative, therefore it had a maximum. Okay, that doesn't really work when you have no information about y. Okay, especially in this is a differential equation that we're not going to be able to solve, even once we learn how to solve differential equations. It's not going to be separable. And really what happens is you don't have enough information about y. Because really what we do with the first derivative test is we make a little manipulation on x on either side of a zero of the derivative, and we see what happens. But we don't know what the y coordinate is going to be, so we can't really evaluate the derivative there. I'm not really even sure how y'all were trying to do that on the test, but I had a lot of people trying. Okay, so what we're going to do is we're going to use the derivative and the second derivative. So y'all try it, I'll freeze it, you can check it working, it's fine. And we're talking about the point 0, 1. So I plugged in 0, 1 into the derivative, and I got 0. It's okay, that's a good sign. It could maybe be a maximum or a minimum. And then I plug 0, 1 into the second derivative. Now, I'm going to, when I'm just looking for the value of the second derivative, I'm going to use this version of the second derivative. Half plus dy dx. I already did the work of calculating dy dx. Okay, so I'm going to say 1/2 plus 0 is 1/2. That's positive. If I have a positive second derivative, it's concave up. And so I draw a little picture of something that's flat and concave up. That looks like a minimum. I say, therefore, f has a relative minimum at x equals 0. Okay, remember that this is not valid justification for the relative minimum. It's these two things, the derivative equaling 0 and the second derivative being positive, that is justifying our relative minimum at x equals 0.